Method of separation of variable. Today we are going to discuss method of separation of variable. As already I have discussed Taylor series and its expansion for various functions. Here we discuss the method of separation of variable. First of all, we recall heat equation. We knew that heat equation is a first order derivative involved partially with respect to time and second order with space variable x. Here the homogeneous condition u0 t and ul or t is equal to 0. Say these are the initial condition. We write the function u, which is of two variable x of t. We can write in separable form as x of x and t of t, capital T of t. These two are x and t variable are separated. Now putting this functions in equation A, that is differentiating with respect to t once and with respect to x twicely, and putting here as we get, see, differentiating we get x and partial t k t. T is a constant, and taking derivative with respect to x partially, partial square x partial x square, using the notation partial capital T divided by n2 partial t is equal to x prime of t kt and x double prime. Separating the variable, we get s2. Now here we see that this left hand side is a function of x and this is a function of t. Both functions are equal. This is only possible that they are constant. Let this constant ratio is equal to minus lambda. Here x double prime over x t prime over k t is equal to minus lambda. X double prime divided by x is equal to minus lambda, and t prime divided by k t is equal to minus lambda. Now separating the variable, x double prime plus lambda x is equal to 0, t prime plus k lambda t is equal to 0. So solving these equations, these are ordinary second order differential equation, and this is ordinary differential equation of first order. Also from initial conditions, we know that u0 of t is equal to, can be written as x of 0 t of t. Here we see that this is a variable, this cannot be 0, so x of 0 is equal to 0. Similarly, ul of t, we can write x of l t of t. Here t of t is not 0, but x of l is equal to 0. Similarly, solving this differential equation per x, we get Tn is equal to natural log of t minus k lambda t. Writing it per n is equal to 1 2 in this form. Here Tn is equal to e power minus k lambda t and minus k in 5 n over t. Now from first part, x double prime plus lambda x is equal to 0. This is 4. X of 0 is equal to x of l is equal to 0. Characteristic equation from 4, we can write d square plus lambda is equal to 0. D is equal to plus lambda under the root iota. Now we write the solution of this equation in c1 e power lambda iota lambda x, or c2 e power minus lambda iota x, which can be written as c1 cos lambda x, c2 sin lambda x. Now from initial condition, x of 0 is equal to 0, putting here c1 is equal to 0. Again x of x is equal to c2 sin lambda under root x, x of l is equal to 0, c2 sin lambda under root l is equal to 0. If we take c2 is equal to 0, then we get trivial solution. For non-trivial solution, c2 is not equal to 0 and sin lambda under root l is equal to 0. Here computing lambda, for lambda under root is equal to L phi, sin inverse 0 is equal to N phi for N1, 2 and so on. Here lambda we denote by lambda n for n is equal to 1, 2, 3 and so on. The solution, x n of x is equal to sin n pi over L, sin n pi over L x for n is equal to 1, 2, 3. Now if we discuss 2, 3 cases, if lambda is equal to 0, then x of x is equal to 0, then u x of t, x of x, t of t is equal to 0. It means that trivial solutions. So, but we are interested in non-linear solution. If lambda is equal to minus alpha square, say lambda is negative, then x sub x is equal to c1 cos hyperbole. If lambda is equal to negative, then this solution will be lambda under root x, and this will be lambda under root x minus lambda under root x, which is equal to cos hyperbolic lambda under root x sin hyperbolic lambda under root x. X sub 0 is equal to 0, it means c1 is equal to 0, x sub l is equal to 0, c2 is equal to 0. It means that lambda is less than 0 is not possible. So the only possibility is lambda is greater than 0, for which n of x is equal to sin n pi over l, n is equal to 1, 2, 3, and so on. Here the solution for keep in mind that the solution for a single particle un x of t x n of x t n of t, but we know that by superposition principle that the solution u1 u2 plus u3 and so on can be written in summation form as cn un x of t n is equal to 0 into infinity cn sin n pi over l x e power minus k n pi over l t. Now using orthogonality and initial condition, let initial condition ux of 0 is equal to f of x. F of x is equal to x and 0 is equal to f of x, and e power 0 is equal to 1 sin n pi over lx. Using Fourier series, 2 over L 0 to L f of x sin n pi over lx dx, 2 over L n is equal to 0 up to infinity cn 0 to L. Taking integration, do not write this, but taking integrations we get cn is equal to 2 over L 0 to L f of x sin n pi over L x dx, n is equal to 1, 2, 3, and so on. The solution of the heat equation, general solution, will be this. This is a general solution where the Fourier coefficient is equal to this one. Now we solve an example. Here an example is given that a rod of 50 centimeter long is immersed in steam until its temperature 100 centigrade throughout. At time t is equal to 0, its lateral surface is insulated and two ends embedded in ice at 0 centigrade. Calculate the temperature at its midpoints after a half of hour if rod is made of iron or here keep in mind that for iron and for concrete the conductivity value k, the k value is different only, nor the solution will be come same. Here the condition u0 of t u 50 comma t is equal to 0, ux of 0 100 f of x. Now solution of 1 is ux of t is equal to 1 up to infinity cn sin n pi over lx e power minus k n pi over lt. Here ux of 0 is equal to f of x, n is equal to 1 up to infinity cn sin n pi over lx. Here ux of 0 is equal to, this is given in the question that temperature is 100 centigrade at initially. So ux of 0 f of x is equal to cn sin n pi over lx. Here 100 is equal to 1 infinity cn sin n pi over 50x. Using the Fourier method to calculate cn orthogonality conditions, we get for cn we get this value. When n is odd, we get this value, and the solution is the. Now using the conductivity value for iron k, we get for iron the required temperature. If we use the conductivity value for concrete, then we get the solution for concrete. Thank you.